That will be better. I think I can share the PPT and then I can discuss. Na? Desktop window. Okay. Let me just see. Open share. What is that? This is. Yes. Yes, Rashman. Open share. Desktop window. What is that? It is not coming. Huh? I think some problem here. Okay. I am not able to share actually. Share permission दिया है कि नहीं उन्हें? I think that whiteboard in screen share. Whether it is coming or not. Okay. My document. MOOC. PPTs. Acha, my screen is getting shared or not? स्क्रीन शेयर हो रही क्या? हेलो, क्या नाम है इसका? नहीं हुआ ना, तो पता नहीं क्यों नहीं हो पा रहा ये जो है। हाँ, स्क्रीन शेयर आया एक डेस्कटॉप विंडो, उसको जब मैं क्लिक कर रहा हूं तो चला जाता है। मेरा ख्याल ब्राउजर का प्रॉब्लम है। एक बार मैं उससे ज्वाइन कर लेता हूँ, क्रोम से ना, अगर इसमें कुछ प्रॉब्लम है। लेट मी ज्वाइन। हाँ, क्या? मैंने ब्राउजर से करता हूँ ना, मैं ब्राउजर से ना। नहीं, ऐसा नहीं, पहले तो हो जाता था, मैंने हमेशा ब्राउजर से ही किया है। अभी जो है इसका अभी देखते हैं, उसमें आ जाता हूँ मैं, इससे आ जाता हूँ। अब I have unmuted, camera unmuted. Okay, now share screen window or type. Okay, fine. Now it is going Chrome window. Okay, so this is a Chrome type Windows entire screen. Okay, now I am sharing this one. Now tell me that whether you are seeing or not. Mechanics of machining, correct? Okay. So Lakshman is there, na? And till now, how many lectures are over? होगा मानता. How many lectures are over?
2 seconds lectures lectures
Okay. Right, okay. So we'll go this one. So mechanics of machining, that we have started that some introduction course. These were the books actually, and there are some other also books. I ask that this उनको बोल दो वहां पे चले जाए. Okay, let me just उनको बोल दो just. राजकुमार BMG. Okay. Now here YouTube होगा. Half. Okay. Let me just YouTube thing is also I make on. Let us see that here. Yeah. Okay. Chalo, ठीक है. They can ask any question, or if they are not having, then I. Yes. Hello. Okay. But YouTube, anybody is joining, 3 watching now. Only the same thing. No, but because I am sharing the entire screen, that also will create problem actually. Okay, yes. And there is a time lag also here. Okay, fine. Now what happens that. Okay. Acha, and problem is that it will be disturbing me. If I open the YouTube, then it will be simultaneously, it will be disturbing me. What is the name of that CET man? Hello? Rekha Hajarika kaha? Rekha Hajarika is my. Rekha Hajarika is okay. Who is speaking? What is your name? Hello? Arnab. See, YouTube is creating problem for me. I just close. If there is any question, then you tell me that. Only you tell. Okay? नहीं तो डिस्टर्बेंस आएगा, डिस्टर्बेंस होगा ना, है ना. वो मैं बंद कर देता हूँ. ये पेस्ट कर देना बाद में ना, या बता देना मुझे ना, है ना. मैं बंद कर देता हूँ अभी उसको बंद कर रहा हूँ. Yes. Okay, Arnab. Is it okay now? Yeah. It is not giving me disturbance. Okay. Lakshman Kumar is here. Okay, fine. So what I am going to tell that, let me just go to this one. Okay. This is lecture 1. Okay. Lecture 1 is already over. That here, what we told that what is machining, definition of machining, subtractive manufacturing process. What are different type of manufacturing processes? Subtractive, additive, and a mass containing like metal forming, joining. Then you have finishing type of. So we are concentrating only on subtractive one. Okay. Although I am showing in the first lecture that some metal forming processes have also been shown. Casting is also shown. Powder metallurgy is also there. Okay. There you have mass containing process, mixing, compaction, and sintering. Then you have additive processes. Our focus is on machining process. So what I told that conventional machining, you apply a wedge shape tool. Why do we apply a wedge shape? Because in order to get leverage, that amplification of the force, if you apply a force of say 1 Newton, you can get a normal force of something like 5 Newton, 6 Newton by adjusting this angle. So that is why we are using this one. So this has been shown here, and then so this was actually talk of the first lecture. Okay. Now yeah. So material is found. what is yes, okay. So this we have already done, and now let us go to this one. Suppose lecture 2. Lecture 2 was what topic? Lecture 2, you have given assignment, basically 2 assignments you have been given. Assignment 1, 0. Where is the assignment 2? Assignment 2. So this is assignment 1, assignment 2. 0 assignment. Why you are taking 2 at 0? Okay. Okay. Assignment 1 and assignment 2. So assignment 2 was on some basic concepts, okay, and assignment 2 was on cutting tool angles, etc. Right? So you have ASA system and all those type of things. Okay. Assignment 2 was on the cutting tool systems. So let me just see that. Say assignment 1 was based on basic concepts, plastic deformation. Like what is the yield criteria? 2 prominent criteria we use in design and manufacturing, that is Tresca and one misses. This was already told. If there is any question you can tell. I will not repeat whole lecture, but I am just showing that main point. Then here, so this is showed that there is some difference between one misses and Tresca criteria, and material deformation takes place because of dislocations. Okay, mostly edge dislocation will cause the slip actually, and screw dislocations may cause twinning, etc. But you know, here we are telling that edge dislocation. So this was the basic of basically the deformation process, and in the lecture 3 we talked about machining process. Okay. So, but before that, in lecture 2, I think we might have told about the this one. Lecture 2 is the plastic deformation, and yeah, lecture 1, lecture 1 was basic mechanics. Here it has been told additive, and this is lathe milling machine. What is mechanics? Yeah, in lecture 1 also many things are there. Elastic deformation, plastic deformation, how you conduct a tensile test on a dark bone sample. Okay. Then you have got fracture. This one, it is this material here, fractures. And then we told that definition of two stress and engineering stress. Engineering stress means force divided by initial area, and two stress means force divided by current area. And we have relation between them. Sigma is equal to S1 plus E, where E is the engineering strain, okay? Because strain is also change in length divided by initial, this one. And then, so we have such type of thing. 2 stress is equal to engineering stress, 1 plus engineering strain. And then there are examples. 2 strain is actually this one, ln L by Li. So here also there is a relation. 2 strain is equal to natural log of 1 plus E. That was also told, okay. Then elastic region yield stress, plastic region. So this is in machining, naturally there will be plastic deformation, and after that material will fracture, okay. Generally, if there is a cast iron type of material, then not much plastic deformation is there. Fracture will be very sharp, and this is what. So this was taught in the lecture 1. In the lecture 2, we discussed mostly the plasticity part, okay. Plastic deformation, classical theory, and up Tresca one misses, and dislocation. So this was told about that dislocation thing, little bit only. Now actual machining topic starts from lecture 3, okay. So what we have told mostly on this one, orthogonal machining, and cutting tool angles, etc. So machining process is explained here. We have single point operation, multi-point, abrasive operation. In single point, you have turning, boring, shaping, planing, and in multi-point, we have got milling, drilling, typing, reaming, harbing, broaching, sign. Broaching is an important process which is used for making sometimes internal gears or internal keyway, in which a big tool broach will pass through the hole and it will machine. Now here that this is turning and this one, now you see the turning is done by the side cutting edge. Little bit in cutting edge is also participating, but mainly side cutting edge, that is primary cutting edge, and it is removing the material like this. So as you can see that the width of the chip is somewhat proportional to depth. This is important, and thickness is like from here to here. Thickness is proportional to feed. Many people confuse in this. They say chip thickness depends on the depth, but the chip thickness is mainly dependent on the feed. Okay, that type of experiment you can do. If you have feed of 0.8 millimeter per evolution, then the chip thickness will be 0.8 only, like that. So same thing happens in this shaper. It is the feed which decides that chip thickness mainly, and depth of cut decides basically the width of the chip. Okay, so this is basically shaping operation, planing operation. Sometimes people are not able to answer that what is difference between shaping and planing. In the shaping, tool is moving, right? Primary motion of the tool is taking place, and feed motion is given to job. Okay, job is, you know, that mounted on the shaper, it is moving this one. But in the planer, you know that the reverse happens. Here the tool is stationary, but whole table is moving. So primary motion is given to the workpiece. That means big. It is used for bigger jobs. So bigger jobs are mounted on the table, and the table reciprocates. Tool remains stationary. Just the reverse of the shaper case. Okay, and intermittent feed is given to tool in this case. Tool is moving here. Job is necessarily not moving. Whole table is not moving. So this is the difference between shaping and planing. Now this is plane milling. Plane milling operation is shown here. You have got a helical type of teeth. Now tell me that why this is helical. So that the load doesn't come all of a sudden on this thing. Load changes somewhat smooth. So that is what we use the helical tooth here, and the load will be little bit smooth, and it is simultaneously, suppose this part gets engaged first and then the other part gets engaged, and then it is the drilling. In the drilling operation, there is a helix, and here also that type of thing happens. This is the tool, and this is a chip. Helical path will help chips to come out. Okay, and these are the cutting edges. There are two cutting edges here, you know, because twist drill, you know, in twist drill. This is a broaching tool, I told. In the broaching, only one motion will be given, and feed motion is given because of the geometry of the broach. Actually, you see the geometry of broach, because the tooth is rising gradually from here to here, from here to here, one by one. So that is why it is able to cut. So you see that there is one big broach, and generally it is operated by hydraulic system, and broach is mounted on a big machine. Basically there is a piston and cylinder. The broach will be moving. You see the broach diameter here, it is very small, and here it is big. So it is tapered shape. So gradually its size will increase. Now you see that it has made broach passed through that. So many internal lines have been made in the job. Okay, so that is what this one. So you have got primary motion, means main cutting motion, and then you have got secondary motion or feed motion. So generally we say that generatrix and directrix. Generatrix is because of the primary motion, and directrix is you are guiding it properly. So that's why, like generatrix in turning operation, you are moving your tool in circular path. Okay, job is moving or tool is moving, means relative motion is circular, and then you are directing it towards axis, so you get a cylinder. Okay, like that you can generate. Then this is a wedge shape tool. This is basically orthogonal machining tool. It is I am showing a very sharp tool. It is 0 nose radius, and you see that it is a rake angle is this, flank angle is this. Flank angle is basically, it is clearance angle, basically you can say. It is relief angle also it is called. Okay, so it is so that the surface should not touch with the machine surface, and this is the rake angle that because it is inclined. So naturally this is the rake surface on which the chip is sliding, and this entire tool is called shank. So orthogonal cutting, that in which the cutting edge is perpendicular to the tool motion. Okay, means primary cutting motion. So it is going, this is the width of the chip, and this is going like that. And it is generally orthogonal cutting is not much used, but many times it is simple to analyze. So we just do approximate analysis by orthogonal model. Oblique cutting is as I have shown here. There are different type of chips. You get continuous chips which are called type 2 chip, which are obtained when you machine some ductile material. And then there are several conditions like high scan speed helps continuous chip, low feed helps continuous chip, large rake angle helps continuous chip, sharp cutting angle. And then you also have got type discontinuous chip. Suppose you are machining cast iron, those are called type 1 chips. Then continuous chip with built up edge. This is type 3 type of thing. So you see built up edge, that means when you are doing machining, then the material got deposited at the tip and it has become very this one joint, and then it is going like that, and this is the tool and this one. So what is the problem with built up edge? First there will be welding at the tip, and after that it will get broken because ultimately the joint is not that perfect. So when it breaks, then it takes away some portion of the tool also. So naturally it causes the reduction in tool life, and also the surface finish also gets spoiled most of the time. So what are the factors that promote built up edge? That speed of the machining. Suppose speed is very high, then built up edge may not fall because there will not be enough time for welding operation to take place. Then uncut chip thickness, suppose thickness is increases, naturally the force will increase and chances of the built up edge will be more. And back rake angle, and then suppose reduction in back rake angle will increase the build. This one, use of cutting fluids. If you use lot of cutting fluid, then chances are that the built up edge will not form because the welding will not take place properly, material will not get sufficiently sharpened. Okay, and the formation of this one. So discontinuous chip is formed machining of the brittle materials or sometimes ductile materials, but at high heat, etc. So this is a table that gives the complete idea. Continuous chip is considered good because continuously material is cutting and therefore surface finish will be okay. Continuous with built up edge, not desired. Discontinuous, you can't help. In some cases discontinuous chips are produced, and discontinuous chips in a way that the chip disposal is actually easy because it is discontinuous, so it will not get stuck up. Continuous chips sometimes get stuck up. So material ductile means continuous, but discontinuous brittle. Similarly, rake angle in continuous large, in discontinuous small. Cutting edge should be sharp, and then here this one, cutting conditions. High speed promotes continuous chip, low feed promotes continuous chip, low friction promotes continuous chip. Cutting fluid, if it is efficient, it promotes continuous chip. Sometimes what we people do that nowadays, people also do that double turning. One PhD student worked with me, he worked on double turning. That means one tool is this side, other tool is going from this side, all balancing the forces. So you can get accuracy, top accuracy job. That is this one. And these are the back surfaces of the generated chip. Okay, so this is you get basically cracks and all those type of things. This is the free surface, chip segmentation, and this is surface roughness of the machined component changes. Cutting speed, as you cutting speed, if you keep on decreasing, initially the surface roughness a bit reduces, but then surface roughness may increase also here because of the built-up edge formation, etc. In the first zone, there is no built-up edge formation. In the second zone, this is like that. Then you may get high surface roughness, but when you increase the cutting speed, then you know surface roughness becomes very less. That's why in most of the machining operation, we have tendency to do high speed machining. In high speed machining, you get double advantage. Surface roughness will also be small, and then after that, you will also get your production time will also get reduced. Okay. As you increase the cutting speed, naturally the temperature increases. Okay. So classification of chip by Ernst in 1938, he classified type 1 means discontinuous, type 2 means continuous, or they are called ribbon type chip. Type 3 means continuous chip with built-up edges. Now, then there are sometimes you get sawtooth type of chip also. Okay. So this is a cyclic type of chips. So you get sawtooth type of this one. They are called also segmental chip. Okay. So an increase in cutting speed has two opposing effects. Strain rate increases, enhances sawtooth formation, but thermal softening reduces it. Okay. So sawtooth chips cause vibrations. They are not good. They increase wear and all those type of things. So this was also in continuous chips. You need sometimes chip breakers, because otherwise the chips will become really long and they will entangle, and they are not good for the safety of the operator. And surface finish also has to be you can get spoiled because the chips will get entangled, and then and chip disposal may also be difficult. So that's why we use chip breakers. Okay, so there are inbuilt type or clamp type. Like this here, you make a group type of thing here. So this is what that people have studied, that chip breaker. That means here they have made some group type of thing, or sometimes they may put a clamp type of thing on the top so that the chips get stuck up and they get broken there. Okay. So these are some results shown by something papers. Okay, this is what this is a chip breaker. Okay. That's what that this was told. Okay, so these are some basics of the machining operation. But let me just go to this one. And then important point was that we told about tool geometry. But let me just see that. Okay, meantime that okay, yes, Lakshman is still there. Okay, and this one. Are there any questions in YouTube or not? Let me just see that. Okay. Okay. Google. Google thing. If there are any questions, then we can answer. Okay. Google. In Google thing, there is no question. Okay. So we will go here. Na? Arnab. उस क्वेश्चन कोई ऐसा उसमें यूट्यूब में तो आया नहीं था चैट में. ओके ठीक है तो लक्ष्मण सुन रहा है तो मैं उसको बता रहा हूँ. लक्ष्मण इज एटलीस्ट somebody is Lakshman Kumar. He may be from south. He's attending that. Okay. So let me continue to this one. And tool geometry was very important topic on which they have given assignment. Do you get the idea how many people submit the assignment? That you don't know. Okay. But some people ask questions also. No? 1 or 2 persons. Okay, fine. Otherwise, they are doing okay, fine. So, tool signature is very important. People ask this question. First of all, you see that what is a cutting tool. Basically, cutting tool means it is a best shape type of thing. You take two surfaces, just like in the village, people use that kulti. What do you call to kulti that in the village? Kulti is done plowing time. What is that called in Assamese? Kunti type thing. So you are X, simple X. You see, it will be of this shape. Why this type of shape is taken? So that the force can get amplified. So here I am showing one figure in which composite material is being cut. So these are carbon fiber directions. Cutting speed is in this direction. This surface is called rake face, and the bottom, this surface is called flying face. Now, if you see that one diagram, this is the sharp cutting edge. It will be cutting. This is also one cutting edge. Okay. So main cutting edge is this. Then rake face, top surface on which the chip will go. In that you may get sometimes some spot type of thing, part hole type thing. This is called crater wear. In English, crater means pit, gadha. Okay. So that is why that you get crater wear, and then you get flank wear on the flank surface. Okay, this is like that. This is also called clearance face. And then so this is a typical tool, but how do we designate properly? You have to define each and everything. So we have showed a typical lathe tool, and we have shown rake face. We are showing that shank nose. There is a nose because the edge will not be totally sharp. Otherwise, it will get blunt very soon. So we give some deliberately, we give some radius. And you see that this surface is called back rake angle, then end relief angle, side rake, side relief, end cutting edge, and then you have side cutting edge and nose. So basically there are 7 elements. Okay. In the front view, you can show two type of things, back rake and end relief angle. And in the side view, you can show two angles. In the top view, you can show 2 angles as well as nose radius. So you have 7 elements. And you have to present these 7 elements in the same sequence so that people should not get confused. So first tell about back rake angle. It is also called top rake angle. Then you tell side rake angle. Then you get end relief angle. Then you tell side relief angle. Then end cutting edge angle, side cutting edge angle. Side comes later on. First comes main. So back, side, end relief, side relief, end cutting, side cutting, and then nose radius. This is a tool signature, typical tool signature. But this is according to American standard. Like that, different countries have got different standards. Usually there are whole common type of standards. So one must know that how to change angle from one standard to other standard. So generally that how do we measure the angles? So there is a tool point reference system in which we make a reference plane which is perpendicular to the cutting velocity. Then we have orthogonal plane and one cutting plane which is passing through the cutting edge. Okay. So one is tool point reference system, oblique or normal reference system, that here one reference plane and cutting plane is same, but this is not orthogonal plane. It is basically normal to the cutting edge. Okay, so this is normal to the cutting edge. So sometimes you have to be understand that whatever rake angle etc. we define, if you change the tool position, then effective rake angle changes. Okay, right? So this point is also very important. Suppose I change that thing. Suppose I lift it up, then rake angle will increase. See here, rake angle is decreasing if I am mounting the job below the surface. Okay. So American system, orthogonal rake system, which is also called continental system, and British system is also there. Then international system is also there. Okay. So in orthogonal rake, there are in each system there are only 7 elements, but and nose radius is common in each. But some change in the angle is there. Like in orthogonal rake system, we have some inclination angle, which is not in the American system. Okay, so that is what that this has been shown. Okay, here inclination angle will also be there. It will be visible in the cutting plane, how much edge is inclined. Okay, then we have maximum rake angle, where one element is maximum rake. Instead of side rake and top rake, we are telling that maximum rake. Okay, so maximum rake means British system. Then normal rake system, inclination angle, and this one. Normal rake system means international. Okay, so we are showing that like that. Now rake angle, how should we do that? These things are very important. Generally, you should keep rake angle between 5 degree to 15 degree for aluminium, 8 degree to 12 degree for steel, and 5 to 10 degree for cast iron. Then flank angle or relief angle or clearance angle, this is between 5 to 12 and 5 to 8. Then cutting edge angle is also there, okay, between 5 to 15 degree or whatever we take. So these are some typical angles as per American system. Or mild steel. It depends what is the workpiece material and what is the tool material. Cast iron, and these are the tools. Okay, aluminum alloys, stainless steel, tool steel, and all those type of things. So this type of system was told, and then what we did that here after introducing these angles. Okay, after introducing these angles, then we have told about this one, I think, conversion of tool angles. So first you see ASA system, American National System, back rake, end relief angle, side rake, side relief, nose radius, and end cutting edge angle, and this one ORS system. Okay, all these type of things have been told. MRS system, NRS system, and then orthogonal rake angle. Now from one system to the other system, how you change? Say orthogonal to normal rake angle. You have to visualize the 3D things here. That is very important. We are trying to show with different figures. Those lectures you listen very carefully, and we are showing that, see, relation between one. Say for example, if you want to find out inclination angle, in American system, inclination angle is not there. But by using this formula, tan I is equal to sin gamma p tan alpha b minus cos gamma p t tan alpha s, you can find out inclination angle. Gamma p is this one, that this is primary angle. This is basically 90 degree minus side cutting edge angle. So you have to find out. Similarly, you can find out orthogonal rake angle also. If you know side rake and you know back rake, then you can find out orthogonal. Principal cutting edge angle is simply equal to 90 minus side cutting edge angle. Okay, so that's what that you have inclination. ORS to NRS, orthogonal rake system, normal rake system. This is the normal rake angle alpha n, and this is alpha 0. So we have told that actually there is relation tan alpha n is equal to cos I into tan alpha 0. That means normal rake angle will always be smaller than orthogonal one. Okay. If it is orthogonal machining, then inclination angle is 0, and in that case normal rake angle will be same as the orthogonal rake angle. Otherwise there will be some difference. Okay, so we have ASA. Now we have given a consolidated set of equations also. How you convert angle from one system to the other system, this is explained here. These are the equations, and vector method, we are also telling that how you can do it by vector method. Okay, by writing that these things in the form of a vector. Okay, PQR, taking that thing, and you can derive. This was basically derivation, and this is I cast this one, and this is P, Q and R, and then you have got basically they are in the same plane, and then you get this one. Okay, so this was, and then this is a formula that how do you know that what is the maximum rake angle? So if you have got side cutting edge angle and you have got back rake angle, so you will have tan square alpha S plus tan square alpha B and take its under root, and this gives you tan alpha M. That means maximum rake angle. Okay, so this was actually told to this one. Okay, and there are some assignments have been done. These assignments are based on these things only. Is it not? No, but we also two assignments have been done. So in the two assignment, not only that, there was this topic also covered, I think. Here. But let me just okay. Yes, this topic was also covered. Yes. So Lakshman, and in YouTube there are no questions, I think. Okay, fine. So in this mechanics of orthogonal cutting, simplified thing that orthogonal, that means cutting is like this. Cutting edge is, this is the chip thickness. Just see chip thickness. This is chip width. Okay. You should not confuse between chip thickness and width. Chip thickness, one side will rub against the rake, other surface will be like that only. So we have said that generally it is a theory that when we cut the material, then the material separates and it shears along this line. That is called shear angle. Okay, that means it is chip will get separated here. Okay, so this is called this one phi, and the material is sliding like this. So this was uncut chip thickness, we say T1, and this is cut chip thickness. Okay, and phi is the shear angle, and T1 by T2 is called the cutting ratio. You see, because of the plastic deformation, chip will expand. Its thickness will become more. So therefore, what happens that cutting ratio is always less than 1. Cutting ratio is never more than 1. Okay. So this is what, and this is the rake angle alpha. So you see that rake angle also is shown. Okay, this angle is very small and we are not studying right now. And we are telling that this is cutting velocity is in this direction. This is cutting speed, and then what happens that here this is T1 and this is T2, and because the thickness has increased in orthogonal machining, suppose width remains same because nothing is going in the width direction, so width remains same, so volume should also remain same. So if thickness has increased, that means the length has decreased. So that's why we can calculate the reduction coefficient also. Final length divided by initial length. So R is known as cutting ratio. Cutting ratio is always less than 1. And 1 by R is known as chip compression ratio, R chip reduction coefficient. Chip thickens, and due to volume constancy, it shortens. Okay. So this is the point. And in 1941, basically Ernst and Marchand, they did a lot of analysis. They made various diagrams. They said, let us see that when the chip is in equilibrium, it gets sheared and it gets broken here basically, alpha. So they are telling what forces are coming. One force will be normal force of the tool, because the chip is pressing the tool is pressing the chip. Okay, so force is like that. Then there is a friction force, because the chip is trying to slide up, so friction force opposes. Then on the shear plane also, chip is trying to go up, therefore shear force is here, and then the normal force there. If the chip is under equilibrium, this resultant force is equal to this resultant force. Okay, approximately. So that's why this is like that. FNR here. This is resultant force. Angle between normal and resultant is called friction angle. That is lambda. And here this is this horizontal, and Fs is shear angle. So he made that one Marchand circle diagram. Okay. By this diagram, why he made a circle? because circle has got a very good property that if you consider any semicircle and you take one diameter like this, you take any point, and if you join this and this, then this angle is always 90 degrees. So since there are many forces which are at 90 degrees, like Fs and Fn, they are at 90 degrees. Fc is cutting force, Ft is thrust force, that is also at 90 degrees. This is F and N, that is also at 90 degrees. So that's why it is becoming like this, and it is convenient to show that graphically. That's all. Otherwise, based on that, derivations have been done, equations have been developed. Without that diagram also you can make the equations, but it is little bit you have to see and you have to visualize. Here it becomes very easy to see. So he made the circle, and it is Fc, Ft, and N, Fs, and all those type of things. So then he find out coefficient of friction mu is equal to F by N, and Fs is basically W times T1 into tau S. Tau S is the ultimate shear stress of the work material, and divided by sin phi. So Fc is equal to this one. Then power consumption during machining is given by this expression. But suppose you say power consumption should be minimum. So this expression should be differentiated with respect to phi and made equal to 0. When you do that, you get some expression for phi. So Merchant gave this type of relation also. That phi means shear angle, friction angle, and rake angle. They are related. 2 phi plus lambda minus alpha is equal to pi by 2. But when he conducted the experiment, then some discrepancy was found. Okay, so he thought that it may be due to pressure dependence on shear stress, like that. So what he said that Bridgman proposed some model tau S is equal to tau 0 plus K1 sigma. That means shear strength itself is dependent on how much normal stress is there. And then you put all these values there, then you find out that 2 phi plus lambda minus alpha will not be pi by 2 or 90 degree. Instead, it will be C is equal to cot inverse K1, where K1 is a material parameter. It is dependent on the material. Okay. So this is what this one. Now, effect of cutting speed and rake angle on cutting force and cutting ratio. In general, if you increase the cutting speed, cutting force decreases, okay, and cutting ratio increases, means it becomes closer to 1. More the cutting ratio, that means you are not spending much energy in deformation, is it not? Cutting ratio is very low, that means the unnecessary lot of change in thickness has occurred. Our objective is not to change the thickness of the material. Our objective is only to machine and separate the material. Okay. So therefore, cutting ratio should be always more than as close to 1 as possible. Suppose you could get 1, it is always better. So if you increase the velocity, then your cutting ratio will improve, means it will go closer to 1. Of course, it will not become 1. And rake angle increases, means cutting force decreases, again cutting ratio increases. That means generally what should we do? That we should employ high cutting force, and we should employ not high cutting force, we should employ high cutting speed, so that my cutting force decreases, and rake angle also should be high. But if you make rake angle too high, then there will be problem. That means then in that case the cutting tool will become weak, because less material will be there. No? Because you have to make the sloping, so you have to cut the material, then you can increase this one. You can visualize it here, that you can just suppose this is the rake angle, this one. Where is the rake? If you want to increase it, that means you have to remove this portion, so the tool will become thinner. The thinner tool will have chance to this one. Okay, so that is what that thing is there. Okay, let me just see that. Okay, now, so this is okay. Any question till now? Any question? Okay, chat box is there here. Chat, nothing is there, no? Okay. Yeah, was invited to the meeting. Fine. So this is yes. So it is okay. Now, okay. So what happens that here? So we propose that this one. So this one and this was what that was there here. Hulls and merchant. So after that, many persons give relation. Ernst and Merchant in the beginning said 2 5 plus lambda minus L5 is equal to pi by 2. But Merchant gave second solution. He said 2 5 plus lambda minus L5 is equal to C, not pi by 2. For some materials it may be pi by 2 like plastic etc. But for others it will be different. Then by strip line method, Lee and Shaffer said that it should be 5 plus lambda minus L5 is equal to pi by 4. And Stabler said that 5 plus lambda minus alpha by 2 is equal to pi by 4. Okay. You can find out the forces by another approach, by specific energy. Specific energy approach means energy consumption per unit volume. That means main cutting force divided by width of chip into uncut chip thickness. That is basically specific energy. Specific energy is some constant times uncut chip thickness to the power minus 0.4. So sometimes you will see that as the size decreases, then the specific energy increases. Okay. So some numerical example was given. Okay. That you know that first, like for Lee and Shaffer relation cutting ratio. This is the numerical example. Coefficient of friction we calculated 0.85. Is it not? Coefficient of friction can be very high. Strictly speaking, Coulomb's model is not proper, but still we use it sometimes for convenience. Otherwise, this is okay. And shear angle is this one. Now, this data has been taken from some media book. To that 45-degree friction force is this, normal force is this. So you see F by N ratio is coming 1.2. Means Coulomb's coefficient is coming more than 1. It is not that Coulomb coefficient cannot be more than 1. It is just coming like that. To be more precise, actually, Coulomb's model is not applicable also, but equivalent coefficient of friction is 1.2. Then suppose a rake angle has reduced, okay. Then in that case, friction force got increased. Normal force also increased. This is like that. Rake angle got further. So you are seeing from this diagram that as the rake angle is increasing, then basically the cutting forces are reducing actually. Okay. But the coefficient of friction is increasing. Okay. Now variation of shear angle with rake angle. This is also shown that 2 rake angle was 45, your shear angle was 39. But when the 2 rake angle was 16, then your shear angle was 27. Shear angle is very small, means more plastic deformation, so not desirable. Shear angle should be little high side only. And this is again, we have seen that relation between this one. How can this knowledge help you in estimating the forces in turning? In turning, that T1 chip thickness is taken as feet times cos psi, where psi is the side cutting edge angle, and width is d by cos psi in orthogonal turning. And condition for orthogonal machining is this: tan I is equal to this, so tan I should be 0. So this is that type of thing. And then there are other conditions also that basically your it should be. There are so many other conditions that means your should be plane strain deformation only. And so mostly this feed force and radial force. Feed force is Ft cos psi, Fr is equal to this thing. Na? So up to this, it has been covered, okay? Up to this only. Na? And then lecture, because after that lecture 7 will be stress and strains and stresses in orthogonal cutting. Na? So same type of thing will continue, like friction force, how it changes with normal force and all those type of thing and different matters. Okay, so that you will be able to do that next time. Okay, so there is no yes, that's what we have done, and almost I think it was 1 hour session, so my time is also now running out. Anybody, if anybody wants to ask question, Lakshman, if you want to ask any question, you can ask. Otherwise, we'll close that. Is there in YouTube, what is the situation? Let me now see YouTube. Maybe I can see that now. YouTube, okay. This one? Okay. Yes. Okay, Lakshman Kumar. Okay, sir, it is visible. Okay, I can text, sir. Okay. Acha, Lakshman is not having mic. Okay. Lakshman Kumar says, okay, he's comfortable. Very good. Acha. Very good. So Lakshman has sent this one a compliment. He says that he is understanding everything. Okay. Yes. Hello, Arnab. Hello. I think we have discussed it because Lakshman sent the message in YouTube. He says that he cannot speak because he is not having mic. उसके पास माइक नहीं है, लेकिन उसको काफी जो है मतलब पसंद आ गया, उसको कोई प्रॉब्लम नहीं है ना. ओके, उसने ही हैज सेंड दिस वन. सो लक्ष्मण कुमार, एंड YouTube में जो रहेगा तो बाद में भी लोग देख सकते हैं ना, YouTube का वो रहेगा. ठीक है, तो कोई अपने कन्वीनियंस के हिसाब से जो स्टूडेंट देखना चाहेगा, मैंने खास चीजें सब बता दी है ना. ओके, क्या क्या इंपॉर्टेंट पॉइंट सभी बता दिए हैं ना. ओके, तो अभी टाइम भी 3:59 हो गया है ना. एक घंटे का ही था ना. ओके, तो फिर अभी बंद कर सकते हो फिर ना. ओके, हाँ ठीक है. ओके, वेरी गुड है ना. थैंक यू ना Lakshman Kumar and other persons for attending this. Okay, and if any doubt is there, you can give me an email also. That is also fine. And exam paper will be easy. That you will be able to do nicely. Okay, yeah, fine. Right. Okay. So you can. This is. This is. For. It is 3:59. It's almost 59 minutes. No, only 1 hour. So we have told, we discussed. Okay, fine. Yes.